Okay, here we need to talk about the differences between what you've learned in pre-calculus and what we are going to learn in calc. So think of this more of a preview of the semester moving forward. So the basic idea of pre-calc was really just to extend your skills in algebra. And we needed to fill in some of the gaps and holes that were still left out throughout your time in algebra. Pre-calculus is really something that keeps things static and non-moving, where calculus is a very different idea. The bridge from pre-calculus to calculus is really done using limits. And so when we think about pre-calc, we think about possibly looking at finding a object that's traveling at a certain velocity, speed. And that object would be traveling at a constant velocity. If we were looking at pre-calculus as it relates to slope, we would talk about it in terms of a line, because slope of a line is constant. If we're looking at tangent lines for circles, or we talk about areas of rectangles or areas of circles or areas of any geometric figure, these could all be things we do in pre-calculus. The key word to what's happening with a lot of these things is the word constant. The idea with calculus is it has to do with changing values. And so we talk about calculus is the mathematic of change. Whether we're talking about changing velocity or changing accelerations or talking about tangent lines and slopes and areas and volumes, we're not talking about these in terms of finding the volume of a specific geometric shape, but changing volumes, changing arc length, changing areas, changing slopes, curvature, etc. These are all things that deal with changing values. And so we use this in a lot of different fields: science, engineering, economics. Lots of real life situations don't deal with constant values, values that are staying the same, but values that are changing. And so calculus will help us do that. The mechanism for how we jump from pre-calculus, or algebra really is what pre-calculus is, to calculus is with something called a limit. And so we think about calculus as the limit machine, okay? And so if we were in calc, some questions we could encounter would be, if we're talking about velocity or even acceleration, we could talk about how the velocity is changing as it relates to acceleration. We could talk about an object that goes fast and then slows down and then speeds up again. I mean, think about when you drive your car. If I drove my car 100 miles, I'm not driving the exact same speed all the time. A normal setup for an algebraic equation or question that would deal with velocity would say, you traveled 100 miles. It took you an hour and 10 minutes to do that. How fast were you traveling? Well, when I say how fast are you traveling, it's how fast on average are you traveling, because you know you're not traveling the same speed the entire time. When you start your car, it takes a while to get the speed up to a certain level. You might turn on the cruise control, in which case you don't stay at that speed all the time. Even cruise control is not 100% perfect. And then eventually you have to stop, which would then slow down. And so when you say your average speed was, I don't know, 65 miles per hour, that's not really how fast you were going. That's how fast on average you were going. But in calc, we could talk about how fast were you going when you hit the 3-mile mark? How fast were you going when you hit the 2-mile mark, etc. And in which case you can figure out, were you speeding up, were you slowing down, and that's the idea of acceleration. So acceleration is the change in velocity. And so that's more of a calculus question. As far as slope goes, we can extend what we know about slopes of lines to deal with slope of a curve. Slope of a curve is constantly changing. If I look at a curve, the slope right here is different than the slope right here, is different than the slope right here. Whereas if I deal with a line, no matter where I am on that line, the slope is the same. So we can talk about that. Tangent line has a very different definition in calculus than what it had in circle. And the idea of areas. Well, you know how to find areas of geometric figures, circles, squares, triangles, etc. But what if I gave you some amalgamous figure like this that's bounded by curves, and I said find the area inside of that, or even then extend that to finding volume? Well, that's far less able for us to do in algebra or even geometry, but we can do it using some very basic mechanisms in calculus. So calculus is really brought down into two main topics. There's the tangent line problem, which we'll spend a good part of the beginning of the semester, first half of the semester dealing with, and then there's the area problem. Now the area problem and the tangent line problem are related, okay? Oftentimes thought of as very different, but then we'll see the relationship between them. This deals with something called a derivative, and this deals with something called an integral. And so thinking about how we bridge the gap between calculus, pre-calculus and calculus is really by using something called a limit. So where we need to start is to talk about limits. So there are multiple ways we can start talking about limits, but first I think the simplest way is to deal with looking at a limit graphically / numerically. And once we get the basic understanding of how a limit works, and sort of estimating the value using a graph or a table, then we can start formally looking at how do we work with limits from a more computational standpoint. So to get things started, we're going to look at a particular function. And so the function we're going to look at is this function right here, which is x cubed minus 1 over x minus 1. Clearly, you should see that x cannot equal 1. The reason why x can't equal 1 is simply because if I let x equal 1, this denominator would be equal to 0. And you can't have the denominator of your fraction equal to 0. It would make the function undefined. And so when I look at the graph of this function, these would be things that you would have learned in pre-calculus, is how to build the graph of certain functions, how to look at how functions behave. This is a rational function, understanding that rational functions have breaks in the graph. Specifically, this one has a break in the graph that is a hole in the graph. And we have this parabola shape to this graph, where we have a hole here, and that hole is occurring where the x value is 1. Specifically, the y value is 3. So this point 1, 3 is a deleted point from this graph. Call it a removable discontinuity, hole, whatever you want to call it. And so looking at this graph, I could ask you, what is the value of, say, f of 1? And you would tell me that it is undefined. Why? Because I can't plug 1 into this function, hence the hole in the graph. It's not part of the graph. This x value does not have a y value. But instead of doing that, what I could say is, what happens to the y value as I get close to an x value of 1? Well, there are two ways I can get close to an x value of 1. I can approach 1 from values smaller than it, so I can use this x value and this x value and this x value. Or I can approach 1 from values bigger than it, which would be this x value, this one, etc. And I can say, well, what is happening with the y values as I do that? This x value would go onto the screen here, would go onto the graph here, which would correspond to this particular y value. This x value would match up with the graph here, which would have this particular y value. This x value would go on the graph here, which have this y value, which essentially, as I move close to this x value, what it has me doing is moving up the graph this way, and the y value is moving up that way. Then if I look at this on the other end, this x value, if this graph extended this way further, this x value would match up with the graph here, and therefore I'd have this corresponding y value. This x value would go on the graph here, this y value, this x value would go on the graph here, this y value. And essentially moving close to the x value in this direction would make me move along the graph this way. And what you could say is, well, the y values here are going this way, the y values here are going this way, and what that happens is, as x is getting closer to this 1, The y values are getting closer and closer to this value of 3, which is the y value particularly for that point that's missing, 1, 3. And so while the function doesn't exist at that point, so if I try to find f of 1, that doesn't mean I can't explain what's happening with the function as I get close to 1. And so that's the basic idea of what limits are all about. Limits are about what happens when you get close to an x value. Can you explain what's happening with the y value? And in this case, the y value, as I approach x from one side, as well as the other, are approaching the same y value, and that would be 3. And so that's the general idea of what we're trying to accomplish with a limit. So there are certain ways that we can write that down. So the notation that we're going to use is this notation right here. So we're trying to find the limit as x gets closer and closer to some value c. So the arrow means x approaches c for a given function. And if we are approaching an x value from both sides and the y value is approaching a single finite value, then that value would be the answer for the limit. So in the previous question, remember the graph looked like this. Yeah, we had this open circle. As I approach this x value of 1 from both sides, the y value was approaching a y value of 3. Remember, on the y-axis, we were coming down to a y value and up to a y value of 3. So we could say that the limit for the previous function was 3. The limit as x approaches 1 for x cubed minus 1 over x minus 1 equals 3. Again, it's extremely important to remember that we are approaching a single x value from two directions, because there are two different ways I can get to 1 along the x-axis, and I'm approaching the same finite y value, a single finite value for my y, then we could say that the answer for the limit is that single finite y value, in this case 3. Again, notice that the function doesn't exist when x equals 1, but that's not what this is about. Limits are about what happens when you get close to 1. You're approaching 1. That's what the arrow is all about. Not what happens when we are sitting at 1, but what happens when we get close to 1 to the function. To the function means for the y values. Another way to kind of describe the exact same thing that was happening in the graph would be to use a table. The table is fairly cumbersome. It's not very easy to work with in that it takes a lot of time. It's a simple concept to understand, but to create these tables, unless you're using some sort of computer software that automatically generates it, which Excel could easily do, doing this by hand would be extremely difficult and just flat out time consuming. So it's not ideal, but it gets the point across. So we think of this function, again, this is our function we're working with, and I know that I can plug certain values in for x. 1 is not one of those values. However, if I plugged in, I don't know, 5 for x or 7 for x, I can get an answer out of that. So what if we just made a table and for this function, and I looked at 1, and I looked at getting closer to 1 from two directions. So let's look at close to 1 from values that are smaller than it. So let's start with 0.75, 0.9, 0.99, 0.999, and see what happens. Well, what I mean by see what happens is let's take 0.75, let's plug it in here for x, and see what kind of answer we get. Again, not the easiest thing to do. If you have a calculator, computer, it's not hard, but trying to do that by hand is not ideal. But this would be the y value we get. That's the function value. Then I'm going to plug 0.9 into this function for x. And this is the y value I get. Again and again and again. So each one of these x values, this is the y value that goes along with it. This x, this is the y. And so as x is getting closer and closer to 1 from values smaller than it, these are the corresponding y values. Well, if you look at each one of these y values, those y values are getting closer and closer to a particular number, specifically 3. Now, is the same thing happening when I get close to 1 on the other end? So as I get closer to 1 on this end, what's happening? Well, if I plug in 1.25 in for x, this is the y value I get. Plug 1.01 in for x, this is the y value. 1.001, this is the y value, etc. This should have an extra 0 on it. 1.0001, this is the y value I get. And again, if you look at these numbers, just look at the pattern of these numbers here. These numbers are getting closer and closer to 3. So as my x is getting closer to 1, my y value in both cases is getting closer and closer to a single finite value of 3. So we can say that the limit as x approaches 1 of x cubed minus 1 over x minus 1 is 3. Now this would require you to fill this table out, which I think if you tried to do this yourself would take you some time. Again, Excel, I could probably get it done in about 10 seconds, but by hand, not ideal, but it gets the job done. All this is just to approximate what you think is happening with the function. None of these are concrete ways of specifically evaluating the limit, but they get you the idea of what we're trying to do. Is that as I approach this particular x value from both directions, I get the same y value that I'm approaching, but both directions, the same single finite y value is occurring. Okay, and so that's a general idea of how limits work, what we're trying to accomplish. In algebra or pre-calc, you would have a function, and you would try to find the function value at a particular number, at 3, at 1, whatever. That's telling you what happens at a value. So you're looking at the graph, you're saying, what's happening right there? What's happening right there? What is the y value? Now we're saying is, if I have a particular x value, I don't care what the y value is right there. How is the function behaving as I get close to this x value? And whether the function exists or not is not necessarily our concern. Our concern is, does it look like the function is getting closer to a single finite value? So when it comes to looking at evaluating a limit, we really have a three-pronged way of doing it. One is the numerical approach, which is constructing the table that we just looked at. The second is a graphical approach. Draw the graph or use, some sort of simulation program that can draw the graph for you. I mean, these aren't always available to us, so your best bet is to make sure you know how to draw the graphs by hand. And see if that can help you determine that as we get close to an x value, do we get close to a particular y value from both directions. And the third one is the analytic approach, which is more the straight computational approach, which is really the best method. The first two methods are more approximating what it looks like your limit will be equal to. It approximates what it looks like the function is approaching. Whereas the analytic approach is a concrete way of seeing what the value is for the limit. So ultimately, we're going to try and go with the analytic approach. But we start off with a numerical and graphical approach so that you get an idea of what the whole purpose is of trying to evaluate a limit. What are we looking for? What are the pitfalls? Is there always going to be an answer for the limit? I mean, these are the things we start with first, and then we kind of go back and say, all right, now that we understand limits, how do we get the values? So when we look at limits, the first thing is to ask the question of, will we always get an answer for a limit? And the answer is no. When you're looking at approaching a particular x value on a function, you may not be approaching a single finite y value in terms of the function itself. And if you're not approaching a single finite value in the function, then that function won't exist, and we would label the limit as does not exist. And so there are really three main times when this would occur. This function right here describes probably one of the more common issues you will come across. And so looking at this function here, absolute value of x over x. With the function absolute value of x over x, and determining whether or not this function exists as we approach 0 is one thing, but we want to look at, does the limit exist? And so first, one way to look at this is to do the graph. And so if you tried to build the graph for this function out, you would say, okay, well, let me start plugging particular x values in. So I plug in, I don't know, 2, 1, half into this function. Well, if it's the absolute value of x over x, if I plugged in 2 here and plugged in 2 here, the absolute value of 2 is 2, and 2 in the bottom, well, I have the same thing over itself, which would give me 1. And I do that for 1, I do it for half. I take the absolute value of any of these numbers, since they're positive, they're just going to be themselves, and the same thing is going to happen in the top and the bottom. And so every one of these particular x values here is going to have a y value of 1. So this has a y value 1, this has a y value 1. And what it gives me is this horizontal line until I get to 0. Now when I get to 0, I have a major problem, because when I get to 0, I get 0 over 0, which is not equal to 0, which is not equal to 1. It's what we call an indeterminate value. There's no value to it. And so 0 does not have a corresponding y value. So if you notice, there's no point above 0 or below 0. I have this open circle here. Notice also when I have negative values, if I take negative 1 and I plug it into this function, negative 1 over negative 1, what do I get? Well, what happens is I get 1 over negative 1, which is going to give me negative 1. If I plug in negative 2, I'm going to get 2 over negative 2, 3 over negative 3. They're all going to give me negative 1 as a y value, so I get this horizontal line down here. And so that quickly built out the graph of this function. Now, as x approaches 0, what's happening? Well, as x approaches 0 this way, the y values I'm working with are down here, and I'm getting closer and closer to a y value of negative 1. As x approaches 0 this way, the y values I'm working with are up here, and the y value I'm getting closer and closer to is positive 1. Well, in this case, as I approach 0 from both directions, I get two different y values, which goes against the idea that I need a single finite y value. So since I don't have a single finite y value that I'm approaching, as I approach 0 from this side and this side, I get negative 1 here, I get positive 1 as my y value here, we would say that this limit does not exist, and we use DNE to represent that. There is no value, single finite value, that this limit is equal to. So that's the main reason why a lot of the limits you're going to look at don't exist. That's not the only reason, though, but it's one of the main reasons. This example brings up another reason why a limit won't not exist, and it has something to do with the idea of a finite value. And so there are lots of different ways to put a break into a graph. One main way to have a break in your graph is with a vertical asymptote, which is pretty severe discontinuity, but nonetheless it's a discontinuity, and that's what's happening here. We have a vertical asymptote sitting right here at the y-axis, which would be when the x value is 0. So as x is approaching 0, okay, we're looking at this function. Now I could say, okay, well, let's go close to 0 this way, let's get close to 0 this way, and what's happening? Well, as I get close to 0 on the right-hand side, which would be values bigger than 0, what I'm essentially doing is traveling along the function this way, going up. So this x value has this y, this x value is this y, this x value is this y, this x value is this y. And notice as I get closer and closer to 0, the corresponding y value for each x is getting higher and higher and higher, to the point where as x gets infinitely close to 0 here, the y value is really large. So it looks like the y value is going to infinity. Same thing's happening on the left-hand side. As x gets closer to 0 this way, this x has this y value, this x has this y value, this x has this y value. As I get infinitely close to 0 on this end, my y value is all the way up here, and I'm going to infinity. Now, unlike the previous question, as I get close to 0 from both directions, I'm doing the same thing on both sides, but I'm not approaching a finite value. I'm approaching an infinite value. And so technically we could say that this function this limit, does not exist. But we're not going to do that. We can go one better than that. While technically it doesn't exist, we're not going to write does not exist. What we're going to write is that this limit equals infinity. Because what that does is it gives me two things. By writing infinity, it's not a finite value and therefore is assumed that the limit does not exist. But two, it's telling me why the limit does not exist. This just tells me does not exist, and that's it. I don't get anything out of it. But this is telling me why it does not exist. It doesn't exist because as I approach 0 from both directions, this function increases without bound. It goes to infinity. Okay? So while does not exist technically is correct, the correct answer to put down for a question like this would be infinity. Now, I'm going to give you another example as it relates to vertical asymptotes. Hopefully we'll clear this up a little bit better. Let me erase some of this out. And so let's say I gave you a function Okay, so let's say I had a vertical asymptote at, I don't know, 3. And let's say on this side, my graph went like that. And on this side, my graph went like that. So that's what my function looks like. And so if I said, what's the limit as x approaches 3 for this function? So I look and say, okay, well, as x gets closer and closer to 3 this way, my graph is doing this, and it looks like the y values are going at the positive infinity. As x gets closer and closer to 3 this way, my graph is doing this, and I'm going to negative infinity. Well, the problem here, as opposed to this one, is I'm not even going to the same infinity. So I'm not going to a single finite value, which I could say then does not exist, right? But I'm not even going to the same infinite value like I was here, positive infinity as well as positive infinity. And so as far as what can I put for this, over here for this one I put infinity as my value. All the while knowing that that means does not exist, but gives me a little more information. Over here for this one, the best I can do is does not exist. Because I can't even write infinity or negative infinity because I'm getting a different direction depending on which way I go to 3. And so while we talk about a function, a limit existing if I get a single finite value, here I was going to both positive infinity, so kind of the single part is taken care of, but not the finite part. Here I'm not even getting a single one. It's a lot like the first question where I was getting -1 from one side and +1 from the other side. So the best I can do here would be does not exist. So vertical asymptotes, as you approach them, generally mean that the limit doesn't exist, but it's just a matter of whether or not you're going to write DNE or you're going to write infinity, depending on whether you're doing the same thing on both sides or different things on both sides. This third scenario as to why a limit might not exist has to do with a function that oscillates. This largely happens with trigonometric functions. So a typical sine function, if I just dealt with y equals, say, sine x, has a wave pattern to it. So it oscillates up and down between +1 and -1. Now this function, the sine of 1 over x, does something a little bit different. It oscillates, but as it gets closer and closer and closer to 0, it goes up and down faster and faster and faster and faster. And same thing if I come in this way. It goes up and down and up and down, and then goes up and down faster and faster and just jumps like that. And so the idea here is if I look at this function and try and figure out as I get close to 0, even if I were to zoom in on this section 10,000 times, this graph wouldn't really look that different. It'll oscillate faster and faster and faster as I go towards this middle where 0 is sitting. And so I can't determine whether there's a single finite value that my y value is approaching, because it'll jump up to here and jump down to here and take all the values in between. And even if I made a table and I put 0 in the middle and I pick x values here and I pick x values here, I plug them in, I look at, okay, what's the y value, what's the y value, what's the y value? My y values are going to be all over the place. They're going to be -1, +1, things in between, and it's not going to be a smooth transition into a single value. It's just going to jump all over the place. And so there's not a single value I can say I'm approaching. So when this oscillation happens, and not just any oscillation, but a very quick oscillation that happens faster and faster as you get close to the middle, that would cause a limit to not exist, and we would write DNA. But this is not a very common one that we're really going to see right now at this level. But it is the third reason why a limit might not exist, so I show it to you. So here's an example of some function. Let's just call this the graph of some function f of x. And so I can ask you a couple questions. One thing I can ask is, find f of 1. So this is an x value of 1 right here. What is f of 1? Well, f of 1 is when I plug 1 into the function, what value do I get? Well, this 1 corresponds to this point right here. That point has a y value of 2. So f of 1 is 2. Okay? The function exists. There is a point that has this particular x value to it. That point sits right here. That point's y value is 2. So f of 1 equals 2. That would be a very simple question I could have given you in pre-calculus. Then I ask you a new question. Find the limit as x approaches 1 for f of x. Not necessarily the same answer. In this case, it is a different answer. And so I say, okay, as x gets closer and closer to 1 from both directions, what's the y value getting closer to? Well, as I get close to 1 from this direction, I'm basically traveling along the graph this way. So this x value has this y, this x value has this y, so ultimately my y values are going like that. As I move closer to 1 this direction, I'm on this point, this point, this point, this point, which is coming down this way, which means my y values are going down. And so the idea here is that as x is getting closer to 1, the y values are getting closer to the y value where this hole is located, which would be a y value of 4. And so if I said, what's the limit as x approaches 1 of this function, the answer is 4. So the function value and the limiting value are different. Sometimes they're the same, but sometimes they're different. I mean, I could have taken this whole thing and I could have just flat out deleted this point right here altogether. Delete, 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 delete. And I said, answer this question. What's f of 1? In which case you couldn't even said 2. You would have just said it's undefined. There isn't a y value, right? When I use this x value, there isn't a y value that's associated with that x. This point right here is missing, and there's no other point sitting right above an x value of 2. So you would have said it's undefined. But the limit would still be 4. So whether the function exists or doesn't exist really isn't necessarily have anything to do with whether the limit exists or doesn't exist. Now, sometimes they're related, but oftentimes they're not. And so when we're doing this, we're saying, what happens when x gets close to 1? When x equals 1, we can find out what happens, but we want to know what happens when x gets close to 1. Sometimes when you get close to a value, it's the same thing as being at that value, but sometimes not. And so that's the whole idea with limits. That was what we were trying to get across when we're working with limits. And now you just see it from a graphical perspective and also from a table perspective. Here's a more complicated graph, but this is the graph of a single function, right? One function kind of gives us all this crazy looking stuff. So I can ask you a lot of different questions here. So let's look at a couple of things. What if I said, what is the limit as x approaches 2 for this function? So looking at this, x is getting closer and closer to 2. What's the y value that I'm getting closer to? Well, as I get close to 2 from this direction, I'm basically traveling along the graph this way because this x value gives me this point, this x value gives me this point, this x value gives me this point. As x goes this way, my graph is traveling towards this open circle. And as x gets closer and closer to 2 from this direction, I'm traveling along the graph this way, all the while traveling towards this open circle, which is sitting at a particular y value. It appears that that y value would be, if this would be 1, that looks like it might be a half. So it looks like the limit as x approaches 2 for this function would be a half, but that's just an estimate. This is no way exact, which is the real main problem with doing limits by looking at graphs. They don't give you exact values necessarily for your limit. They give you an idea of how the function is behaving, and they give you an estimate as to whether or not the limit exists and what that value is, but you never really get the exact value necessarily. It depends on your precision with your graph, etc. But it gives you an idea of what's happening. So if I said what's the limit as x approaches 2 using this graph, we would say that the limit is a half. Okay. Let me give you another one. What's the limit as x approaches 0 for this function? Well, as x gets closer and closer to 0 this way, the y value I'm getting closer and closer to would be whatever this y value is, which is again at a half. As I approach 0 from this direction, however, the y value I'm getting closer and closer to is this y value, which is 4. And so I don't approach the same thing. And the key is you have to be getting closer to the same y value from both sides. Since I'm not getting closer to a single finite y value, I would say that this limit does not exist. Now, to change that up for a second, if I went back to this first question, I said find f, let me get a different color, find f of 2. There is no function value when x equals 2. If you notice, there's no point sitting anywhere above the 2. So this is undefined. Undefined. Okay? If I said find f of 0, there is a point that has an x value of 0, and that point sits right here. And that x value is associated with a y value of 4, so f of 0 equals 4. But this question and this question are different. This question and this question are different. And we're trying to find the answer to the limits. In pre-calc, you were just trying to find the value of the function. All right, let's try one or two more. Let's see, how about the limit as x approaches -2 for this function? So let's erase some of this business. So here's -2. I got to approach from both directions. As x approaches -2 from the left side, from smaller than -2, the function's doing this. As x is approaching -2 from the right-hand side, the function's doing this. Am I approaching a single finite y value? And the answer is no. Here I'm going down to -infinity. Here I'm going up to +infinity. As far as what's the best answer I can give here, DNE does not exist is the best answer. I can't even write infinity or negative infinity. The best I can do is write dne. If I looked at, okay, what is f of negative 2, I would also say it's undefined. So again, here the limit existed, but the function didn't. Here the limit didn't exist, but the function did. Here the limit doesn't exist and the function doesn't exist. So I'm just trying to hit home the point that these are different questions. Whether one exists or the other one does exist doesn't necessarily mean the same for the corresponding question. One more. So last one, limit as x approaches 4 for this function. So here's 4. X is getting closer and closer to 4. What's happening to y? Well, as I get close to 4 this way, my graph's doing this. As I get close to 4 this way, my graph's doing this. So it appears that the y values are going towards infinity on both sides of 4. So I could say that this limit is approaching infinity, which all the while I know does not exist, but I'm going to write infinity for this one because I'm approaching the same thing from both sides. If I said what is f of 4, the answer is not infinity, because if you look at 4, 4 gives me a y value right here of 2. But f of 4 and the limit as x approaches 4, again, different questions. Pre-calc, intro to calc. Okay? So hopefully that clears up all the different things that could go on graphically and whether or not a limit exists, doesn't exist. Are you approaching a single finite y value as you approach a single x value from both directions?